In our previous section, we had seen about power available. Let us move on to range and endurance in this section. Range is technically defined as the total distance measured with respect to the ground by the aeroplane on a tank of fuel. A related quantity is endurance, which is defined as the total time that an aeroplane stays in air on a tank of fuel. In different applications, it may be desirable to maximize one or the other of these characteristics. The parameters that maximize range are different from those that maximize endurance. They are also different for propeller and jet-powered aircraft. Let us look at the physical consideration of a propeller-driven aircraft. One of the critical factors influencing range and endurance is a specific fuel consumption, the characteristics of the engine. For a reciprocating engine, specific fuel consumption, commonly abbreviated as SFC, is defined as the weight of the fuel consumed per unit power per unit time. As mentioned earlier, reciprocating engines are rated in terms of horsepower, and the common unit of specific fuel consumption are LBO fuel by shaft brake horsepower R, where bhp signifies shaft brake horsepower. For a jet aeroplane, a specific fuel consumption is defined as the weight of the fuel consumed per unit thrust per unit time. Note that thrust is used here in contradiction to the power as in the previous case for a reciprocating engine propeller combination. The fuel consumption of jet engine physically depends on the thrust produced by the engine, whereas the fuel consumption of a reciprocating engine physically depends on the brake power produced. It is this simple difference that leads to different range and endurance formulas for a jet aeroplane. Thrust-specific fuel consumption, abbreviated as TSFC for jet engine, is commonly given as LBO fuel by LBO thrust R. Maximum range and endurance on propeller-driven aeroplane. First, consider endurance. To stay in air for a longest time, common sense says that we must use a minimum number of pounds of fuel per hour. On a dimensional basis, this quantity is proportional to the horsepower required by the aeroplane. Since minimum pound of fuel per hour given maximum endurance, we quickly conclude that maximum endurance for a propeller-driven aeroplane occurs when the aeroplane is flying at minimum power required. This condition is shown in the graph. Further, we have already proved that the minimum power required corresponds to the maximum value of CL to the power 3 by 2 by CD. Thus, maximum endurance for a propeller-driven aircraft occurs when the aeroplane flying at a velocity such that CL power 3 by 2 by CD is maximum. Now consider the range. To cover the longest distance, say in mile, common sense says that we must use the minimum number of pounds of fuel per mile. Now, assuming that V infinity is in miles per hour, minimum pound of fuel per mile are obtained with a minimum horsepower required by V infinity. This minimum value of horsepower required by V infinity precisely corresponds to the tangent point shown in the graph, which also corresponds to maximum L by T. Hence, we can say that maximum range for a propeller-driven aeroplane occurs when the aeroplane is flying at a velocity such that CL by CD is maximum. Determination of range and endurance. For equations, range is equals to integration W1 to W0 V infinity dW by Cp, and endurance is equals to integration W1 to W0 dW by Cp can be evaluated graphically. These two graphs shows the range and endurance respectively. Range can be calculated by plotting V infinity by Cp versus W and taking the area under the curve from W1 to W0. Analogously, the endurance can be calculated accurately by plotting inverse of Cp versus W and taking the area under the curve from W1 to W0. These two equations are accurate formulation of range and endurance, where E is for endurance, dW is change in weight of aeroplane, P is the fuel consumption, P is the engine power, R is for range. They can include the entire flight, take off, climb, cruise and landing as long as the instantaneous value of W, V infinity, C and P are known for each and every point along the flight path. equation here is the Brankett endurance formula where E is in seconds. Looking at this equation, we can say to maximize the endurance of the reciprocating engine, propeller-driven aeroplane must have the highest propeller efficiency, lowest specific fuel consumption, highest fuel weight, where W0 is equals to W1 plus WF. Flight at maximum CL to the power 3 by 2 by CD. For a maximum endurance, we must fly at maximum CL to the power 3 by 2 by CD. Flight at sea level becomes endurance is directly proportional to rho infinity to the power 1 by 2, and rho infinity is the largest at sea level. It is interesting to note that subject to our approximation, endurance depends on altitude, whereas range is independent of altitude. For maximum range, this is the formula, which is the classical formula in aeronautical engineering. It is called a Brankett range formula. Looking at this equation, we can say to maximize range for a reciprocating engine, propeller-driven aeroplane, we need largest possible propeller efficiency, lowest possible fuel consumption, highest ratio of W0 by W1, which is obtained with the largest fuel weight. Now let us look at an example to estimate the maximum range and endurance of a CP1. Specific fuel consumption C is given as 0.45. The variation of CL by CD is equal to L by D was calculated versus velocity. The variation of CL to the power 3 by 2 by CD can be obtained in the same fashion. The results are plotted in this graph. From the graphs, we can see that maximum CL by CD is equal to 13.62 and maximum CL to the power 3 by 2 by CD is equal to 12.81. These are the results pertaining to the aerodynamic of the aeroplane. Even though the preceding plots were calculated at sea level, the maximum values of CL by CD and CL to the power 3 by 2 by CD are independent of altitude, velocity, etc. They depend only on the aerodynamic design of the aeroplane. From the parameters of CP1, we know the weight, gross weight, fuel capacity, and empty weight of CP1. Hence, by substituting that in the range formula, we get that range is equal to 6.38 into 10 to the power 6 feet. Again, substituting all the parameters in the endurance formula, we get endurance is equal to 5.18 into 10 to the power 4 seconds. Maximum range and endurance on thrust required curve for a jet engine. The maximum endurance of a jet aeroplane occurs for maximum pound of fuel per hour, as same as for propeller-driven aircraft. In a steady, level, unaccelerated flight, the pilot has adjusted the throttle such that the thrust available just equals to the thrust required. Therefore, minimum pound of fuel per hour corresponds to minimum thrust required. Hence, we can conclude that maximum endurance for a jet aeroplane occurs when the aeroplane is flying at minimum thrust required. This condition is shown in the graph. Furthermore, the minimum thrust required was shown to correspond to the maximum L by D. Maximum endurance for a jet aeroplane occurs when the aeroplane is flying at a velocity such that CL by CD is maximum. Maximum range occurs for a maximum number of pounds of fuel per mile. Hence, minimum thrust required by V infinity corresponds to maximum CL to the power 1 by 2 by CD. In turn, we conclude that maximum range for a jet aeroplane occurs when the aeroplane is flying at a velocity such that CL to the power 1 by 2 by CD is maximum. Maximum endurance of a jet aeroplane formula is given here. Note that from this equation, the maximum endurance for a jet aeroplane, we want minimum thrust specific fuel consumption, maximum fuel weight, flight at maximum L by D, which confirms that maximum endurance for a jet we need to fly such that L by D is maximum. This is the equation for maximum range of jet aeroplane. Hence, from this maximum range of jet aeroplane equation, we can conclude that we require minimum thrust specific fuel consumption, maximum fuel weight, flight at maximum CL to the power 1 by 2 by CD is for maximum range. A jet must fly at a velocity such that CL to the power 1 by 2 by CD is maximum. Let us estimate the maximum range and endurance for a CJ-1 aircraft. Here the specific fuel consumption is given as TSFC is equals to 0.6. Making this in a consistent unit, we get 1.667 into 10 to the power minus 4 per second. We are also aware of all the parameters of CJ1 from our previous sessions. Again, the variation of CL by CD and CL to the power 1 by 2 by CD can be plotted versus velocity from the given graphs. From the graphs, we can see that the maximum CL to the power 1 by 2 by CD is equals to 23.4 and the maximum CL by CD is equals to 16.9. Substituting these parameters in the range equation, we get R is equal to 6.06 into 10 to the power 5 feet. Again, substituting these parameters in the endurance formula, we get E is equals to 4.79 into 10 to the power 4 second. I hope you would have understood range and endurance. Let us move on to takeoff performance in our next session. Thank you.